Okay, in this video we're going to look at creating a Thevenin's equivalent circuit. So it's a three-step approach. So first of all, we'll calculate the voltage open circuit, which is just the voltage between our potential divider, then the current short circuit, and then the equivalent resistance. Let's just write those down. Okay, so let's put that together in a example circuit. So first of all, step one, we're going to calculate the voltage open circuit. So that's when we say that there is no load there. So we're just effectively calculating what the voltage is at this point here. Okay, so we can do that using the ratio method, or we can use the three-step approach. I'm just going to use the ratio method. So I make that 7.2 volts that we've got there with no load connected, voltage open circuit, no load connected. Okay, so that was step one. Okay, step number two then is we're going to calculate the current short circuit. So as we're shorting out this load, so effectively we're making the load have zero resistance. So there's a piece of wire going down there. So R2 disappears. So we're just left with all of the voltage there across R1. So we're going to have 12 volts divided by 4 kilo ohms. Okay, gives us 3 milliamps. And step number three, equivalent resistance. Is our voltage open circuit divided by our current short circuit. So we've got 7.2 volts divided by our 3 milliamps. Gives us 2.4 kilo ohms. So we're now in a position now we can draw the equivalent circuit. Now, just one curious thing that we could have actually, just to double check our result, if you were to put these two resistors in parallel, so you're bending the circuit round, then actually you end up with the same value. A 4K in parallel with a 6K gives you 2.4K. It's just something that you might use to double check your answer. Okay, let's draw our equivalent circuit. It's a bit like this. So we've just drawn our equivalent circuit here. So we've got our equivalent circuit is saying we've got 7.2 volts with a 2.4 kilo ohm equivalent resistance, and then our load resistor. Okay, and that's it. That's all we need to do. You don't even actually need to label those up, but you just need to use those two values, the equivalent resistance and the voltage open circuit. Okay, we've got a couple of questions that we could get asked then to associate with our load. Okay, so quite a common question that could get asked is if our load was something like a phone that required 5 volts, 5 volts across it to make it work, then we could say, well, what is the minimum resistance that can be for to be 5 volts across here? Okay, because obviously the resistance of our load is going to affect the voltage that we have across it. The larger size resistor, it's just going to be more voltage across it, but the smaller that resistor gets, the less this voltage is going to be. So let's just write down that question. Okay, so with that then we then say, well, okay, so if that's going to be the case, therefore we want 5 volts across the load, means that we can say then the rest of the voltage using Kirchhoff's laws, that is going to be 2.2 volts, therefore across our equivalent resistance. We now know a voltage across a known resistance, so therefore we can work out what the current flowing in that circuit is going to be. So let's just work that out. So 2.2 volts divided by 2.4K. So rounding up, we've got 917 microamps. Okay, so that same 917 microamps is also going to be flowing through our load, which has got 5 volts across it. So then that will tell us our load resistor value. Okay, so load resistance value. So always comes down to Ohm's law, everything. So voltage divided by current. So we've got 5 volts divided by the 917 microamps. I'm keeping the original figure in my calculator, so I don't introduce any rounding errors. So we end up with 5.45 kilo ohms. Okay, easy peasy.